Hey guys, welcome back. I'm glad to see all of you here again. The last time we discussed thermodynamic work and we talked about the concepts of thermodynamic work. Then that's the integral of PdV. Then we are looking for a function P with respect to V. And also we talked about the sign of the work. If the volume increases, then we have a positive work. If the volume decreases, then we have a negative work. Then if we don't have volume change, then no thermodynamic work. And also we talked about the specific work, which is work divided by mass. So if you haven't watched the last video, so watch the last video first. Then today we are going to keep going on thermodynamic work. Then we are going to take a look at work in processes. Then let's get it started. All right, then this is work in processes. Then we are going to take a look at thermodynamic work in Isochoric process, Isobaric process, and also isothermal process, and also a general form for polytropic transformation. Then this is the formula sheet that you will have on your exam. Then if you know it's an isochoric process, then no work. The isobaric process, you can use this formula right away. Then we define this as formula 1. And if the problem says it's an isothermal process, then you can use this formula right away. And we define either of these two as formula 2. Then if it's a general polytropic transformation, then you can use formula 3 here. Then we are going to take a look at how those equations coming from. Then the first one is isochoric process. The isochoric process means volume doesn't change. So no volume change turns out to be this term is 0, so no work. So for isochoric process, then no work done. Simple enough, right? Okay, then let's look at the second process, isobaric process. Then isobaric means pressure is a constant. Then work is the integral of PdV. Since pressure is constant, then we can take the pressure out. Then integrate 1 here. Then turns out to be it's V from V1 to V2. Turns out to be this is the work for isobaric process. Then you can only use this formula when it's an isobaric process. So only for isobaric process, then the pressure is a constant, then you can use this formula. So only for isobaric process. Then the next one, you might think about isothermal process. But instead of introducing isothermal process right now, let's take a look at polytropic transformation. So polytropic transformation is defined as PV power to N is a constant. Then N is polytropic exponent, which means if the process, you can find a relation that PV power to N is always a constant, then we define those processes as a polytropic transformation. So if the process is a polytropic transformation, then the pressure is going to be C divided by V power to N. Then we are going to discuss the polytropic exponent. So when N equals to 0, then turns out to be the denominator is 1. So P equals to C. So when pressure is a constant, then it's an isobaric process. The next one is when N equals to 1, then the denominator is volume. Then we put it on the left side. Then turns out to be PV is a constant. Then also previously we learned thermal EOS. as one of the applications, it's ideal gas law, PV equals to RT. Then we can times mass on both sides, then turns out to be P capital V equals to MRT. Then M, which is mass, won't change. Then R is a gas constant, won't change either. So if MRT is a constant, then turns out to be the temperature has to be a constant. Then when the temperature is constant, then that's a isothermal process. All right, then turns out to be when N equals to 1, that's an isothermal process. Then let's still start up the definition of thermodynamic work, the integral of PdV. Then we are going to replace P something with V so we can integrate. So P is C divided by V, then plug it in here. Then turns out to be it's this formula, then C is a constant. So take that out, then integrate 1 over V. Turns out to be its natural log. Then we plug in and then the upper and the lower interval. Turns out to be it's this expression. Then keep in mind for isothermal process, then PV equals to constant because PV equals to RT. So RT is a constant. Then for this expression here, we could replace C with either P1V1 or P2V2 or P3V3. So it turns out to be for isothermal processes, then the work done could be either P1V1 times natural log V2 over V1 or P2V2 natural log V2 over V1. So this is for isothermal process. Then the next one, we are going to take a look at the general form of polytropic transformation when N is anything except 0 and 1. So this is the general form of thermodynamic work. Then we are going to plug in P and have a formula P with respect to V. Then rearrange this formula to be this term, then plug in P into the formula. Then C is a constant. Then turns out to be this form here. Then we integrate V power 2 minus N. Turns out to be this expression here. Then we plug in the upper and the lower domain. Then turns out to be it's this form here. Then we are going to plug in C here. So put in the C into the formula, and once again, C could be either P1V1 power 2N or P2V2 power 2N. Then since this is V2 here, so we are going to put P2V2 power 2N. And the other term, it's P1 here. So we put P1V1 power 2N. Then turns out to be it's this expression here. So for a general polytropic transformation, then the work is this expression here. Then as the review, if it's for an isochoric process, so no work done. If it's an isobaric process, it's our formula 1, P times V2 minus V1. And if it's an isothermal process, then this is the work done. We denote this as formula 2, which is P1V1 natural log V2 over V1, or P2V2 times natural log V2 over V1. And if it's a general polytropic transformation, then we use formula 3, then it's 1 over 1 minus N P2V2 minus P1V1. All right, so this is all we have for today's part. Hope you learned a lot. Then we'll see you next time.